Hi guys, welcome back to Data Every Day. Today we're looking at a data set of bee images. So these are images of honeybees carrying pollen and not carrying pollen. And you can see these images are not in this typical directory structure where you have I think the name, the NP stands for no pollen, and there's a P to stand for pollen. But I'm just pointing out that they're not in the typical directory structure where you have the parent folder containing the class name. Instead, what's given is a data frame or a CSV file containing the file name and the class for that file. So we're going to use this. Sometimes, I construct my own data frame that looks like this, but they provided it for us. So let's go ahead and get into the notebook. I'm going to be using NumPy, pandas, and the path object from pathlib for working with the data. For visualization, I'll be using pyplot and seaborn. And for preprocessing, I'll use the train test split function from scikit-learn. We're going to build the model, which will be a convolutional neural network using TensorFlow, actually Keras. And for metrics, we will use the confusion matrix and classification report from scikit-learn. Before we proceed, I just want to point out I do have GPU acceleration enabled, which will speed up the training of the model. Now, I don't think it's so important to use in this situation since there's only a few hundred images, but I'll still keep it enabled anyway. All right, let's go ahead and import everything, and we're going to load in the data using pandas.read CSV. So this data is actually just the file names combined with the classes for each file, and we can get that. We get the file path to it up here, which is pollendata.csv. Let's go and pass that in and take a look. So I don't want this column here, it's just a duplicate index column, and we could go and drop it, but we can just make it easier by typing use calls and then just using file name and pollen carrying. And that will automatically drop it for us. We can also check data.info, although I doubt we would have missing values in this sort of data set. Yeah, nothing. And let's start pre-processing. So by pre-processing, all I really want to do, before we pass this data frame into our generator, we're going to need file paths instead of just file names. So what we'll do is we'll turn these file names into file paths, and we'll also do a train test split so that we have a train set and a test set. So I'm going to create a function called preprocessdf, pass in the data frame, and we'll start by creating a copy of it so we don't modify the original. First thing I want to do is change file names into file paths. So what I'm going to do is pass in an image path along with the data frame. That will be the path to the images folder, or the folder containing all the images. Now, there's a nice way, easy way to do this. If we take one of these file names and we store it as a string, there's actually okay, so if we were to get our image path, that would be this one here. Let's copy that. It's actually, I have to type it in, pollen dataset / images. So that's our image path right here. What's nice about the path object from pathlib, I mean there's many nice things about it, but one nice thing we can do is if we turn one of these file paths into a path object, we can then use the division operator to actually basically append this path to that path. And one of them can be a string, it doesn't matter. As long as one is a path, you can see it will then actually place that on the end and use the slash as if it were like the slash in a directory name. And this will easily allow us to convert all of the file names into file paths. So in here, let's do that. We're going to take the file name column, and we're going to apply a lambda function to it. A lambda function that for every x, where x is a given file name, we're going to do path of x, and then we're going to do image path divided by the path of x, like we have up here. So we pass the image path in through the argument, and then we convert it to a to the full path. However, this is a path object, and if we're going to pass it into TensorFlow, we need to make sure it's a string. So let's do as type string afterwards. Alright, so if we return df and take a look at the results, let's call it image df and use preprocess df, passing in data, and the image path here will be this thing. So right there. Oh yeah, let's take a look at it. You can see we now have the full file path for each example, along with the label. And this is the format of data frame you need if you're going to use the image data generator from Keras. So last thing I'm going to do is then do a train test split. So we are going to get two new data frames out of this, train df and test df. And we'll use the train test split function from scikit-learn. We're just going to pass in our data frame, give it a train size. Let's say 70% goes to the train set. And then we'll keep shuffle equals true, so it'll shuffle the data before it makes the split, and give it a random state as well, so we can reproduce the shuffle. And then let's return these two sets of data and get them back over here. And we can look at train df, should just be 70% of the original data frame. Alright, test df would be the other 30%. Okay, now let's load in the data using the generators. So we're not actually going to load them in. What a generator does is it sort of provides a specification for how the data will be loaded one batch at a time. So I'm not sure if it would be a problem since we have such a small number of images. But if we were to scale this data set up, we would want to use a generator, because essentially what happens if you load all the images at once, you're going to run out of memory. So the generator will load one batch at a time, it'll train on the batch, and then recycle the memory afterwards to make way for the next batch. So this comes from tf.keras.preprocessing.image data generator. And in here you can pass in any sort of image augmentation things you like flipping, scaling, zooming, brightness shift, width shift, height shift, etc. Rotation. I'm not going to do it right now. I'm just going to rescale by a factor of 1/255. And since the pixel values are on a range of 0 to 255, if we divide every pixel value by 255, that has the effect of scaling the range of values down between 0 and 1. And then we'll call this train generator. And we'll do the same thing for test generator. So they're both the same. However, for the I do want a validation set as well. And the generator has a nice feature, validation split, which we'll only use on the train generator. But this allows us to save 80% of the data for training and the other 20% for validation. So we made our two generators. Now we're going to specify how the data should come in. So these generators have a nice function called flow from data frame. And then we specify a data frame here, which would be our train df for the train set. And we specify an x column, which is the column containing our file paths, which I believe is called file name, and a y column, which is the column containing our labels, which is pollen carrying. At this point, I realized though TensorFlow actually will require string labels coming in. So I could go and convert one to just convert these to strings, like 1 as a string or 0 as a string. But I think it'd be nicer if we gave it some actual names. So let's create text labels for the images. So we're going to take the pollen carrying column, and we're going to use the replace function on it. .replace, and this allows us to give a mapping that will map the old values to the new values. So if we have a 0, it will become no pollen, and if we have a 1, it will become pollen. Now you can see those are the text labels, and we should be ready here. Okay, so a few more things we have to specify. The target size This allows us to resize the images so that they're all the same size, which is important. I think it said these are high resolution images. Yeah, so we don't need high resolution images probably for our purposes. We can use the standard size of 224 by 224 and then give it a color mode of RGB. So that means it has 3 color channels coming in. We'll also specify a class mode, which will be binary in this case since we have 2 classes. A batch size, which let's make it 32. We'll turn shuffle on, so shuffle equals true, because this is the train set, so we definitely want to shuffle the images during training. And then we should give it a seed, a random seed, so it's just a random state, so we can reproduce the shuffle. And then we have the subset argument, which allows us to target which part of this validation split we specified earlier. So we do training for training, validation for validation. We can then copy this over and do the same thing for the validation set, just changing the subset. Alright, I'm going to store the result of this flow into train images and store the result from this one into val images. Then we'll also do a test flow, so test images. This time we're going to flow from test generator, which is the other one we created. We're also flowing from test df. Everything else is the same except I want to turn shuffle off. Since we're just going to be evaluating this, we don't have to shuffle it. Alright, so it told us now found 400 validated images belonging to 2 classes. So this is the training set, the validation set, and the test set. Alright, let's build the model now and begin training. So I'm going to create an input layer with tf.keras.input. This is the actual image data coming in. So the shape here is going to be 224 by 224 by 3. 3 being 1 for each color channel. And then we're going to pass it into a convolutional feature extractor. So convolutional layers basically look at regions of the image and generate new 2-dimensional features based on the relationship between pixels. So what I mean is we have, it's called a kernel, or it's like a sliding window that goes across the image. And the kernel has some weights associated with it. And at each time step, the kernel's weights are multiplied with the pixel values. And then everything in the kernel, within that multiplication is summed up, and that value is sent to a new pixel in a new 2-dimensional feature. And for each time step it does this, and it generates the new 2-dimensional feature across the whole image. So each one of these 2-dimensional features is sort of the result of the kernel convolving across the image, or it's basically information about relationships between pixels. So let's do that. We'll call this layer x, and that will be tf.keras.layers.conv2d. We have to specify the kernel size, so that's how big of a window we pass through. Let's do 3 by 3, which is the default. And we also specify the number of filters. So filters is how many full passes over the image are we going to make. For each full pass, we're going to use a different set of weights, and we're going to generate a new 2-dimensional feature. So if I use 16 filters, we're going to make 16 full passes over the image, each time generating a new 2-dimensional feature. So we'll end up with a 3-dimensional output with 16 2-dimensional slices where each one came from a different pass over the image. Alright, and then we will give this an activation function as well. So let's give it a ReLU activation, pass in the inputs, and then I want to duplicate this over because we're going to do this again. Just pass in x this time, and we're going to change the filters. We're going to bump up the number of filters. So one way you can think about this is as we do this, this one is sliding a window over the new features. So the first convolutional layer is sliding a window over the actual image, but the second convolutional layer is sliding a window over these new features we've created. So what you end up, this isn't necessarily what's happening, but one way to interpret what's happening is that the first one is looking at low-level features in the image, like lines and curves and corners and points. And the second one is looking at higher level features. So things like maybe circles or shapes, or constructing something using the original features we extracted. So hopefully by the end of this, we will end up with some sort of descriptive or informative features about the image. So maybe we'll have a feature that tells us if there's a pollen sac or a collection of pollen on the bee, which would be useful for making predictions. So after each convolutional layer, we're going to do max pooling. So that's a max pool 2D layer, and what that does is it reduces the dimension, the resolution of the data, by basically also sliding a window across the data, but at each time step we'll just pools based on the maximum pixel value in that window. So what you end up doing is shrinking the image, and the main reason for this is it allows the next convolutional layer to look at more of the image, to look at a larger region of the image, or get a more general sense of the image. You are losing information though with a max pool layer, and that is why some people disagree with the use of convolutional networks. However, you cannot argue for their results. You cannot argue with the results. Okay, so now we've pooled down twice after each convolution, and what we end up with is what we hope to be some useful set of features. Now these features are still three-dimensional. If we look at this now, if we look at what the output of this is, you can see we end up with a 54 by 54 by 32 output. So this 54 by 54 is coming from the original size being pooled down twice, so we get a smaller dimension. And the 32 comes from the 32 filters of the last convolutional layer. So this convolutional layer made 32 two-dimensional features, which were based on the original, based on the last layer. And then that got pooled down even further. But we still have 32 of these two-dimensional features. So there's a few things we can do here. One is we could flatten this out to be one-dimensional, because we do need one-dimensional if we're going to do classification. Another thing is, what we're going to do is do global average pooling. So tf.keras.layers.global average pooling 2D. And what that will do is it will take this shape and average over the first two dimensions, so that we end up with a single 32 outputs, where each of these 32 values is the average across both dimensions. So we do get one dimension this way as well. And it's sort of up to you if you want to use this. You should try out both and see which works best. This gives you fewer features as to compared to flattening it. And I guess you do lose some amount of information, but by taking the average, you're retaining a lot of the information that is contained. Alright, so now we have a one-dimensional output. We're going to use this as the input to a standard neural network. So we're going to use two dense layers with 128 neurons, a ReLU activation function. We'll pass in X, and we'll just copy this over. So this is the classifier part. This whole first part is just to extract features. We end up with 32 nice features, and then we use those 32 features as the input into a two hidden layer neural network, and then we get our outputs, which will also be a dense layer with one output and a sigmoid activation function. So this one output is basically the probability of there being pollen in the image. We pass in x, and we'll create the model. So tf.keras.model. The inputs are inputs, and the outputs are outputs. Then we'll compile the model. So we'll use an atom optimizer. For loss, we'll use binary cross entropy. And then for metrics, let's just use accuracy. We'll do a full analysis later. And then we'll fit the model and store its results in history. So model.fit. We're fitting on the train images, which that comes from the generator, right? So it has both the image data and the labels associated with it. Then the validation data is going to be val images. And these both come from the same data frame and the same generator, just using different splits. And we'll give a number of epochs. We don't have to specify the batch size here since we did it up here. Alright, so we'll train for 100 epochs and use an early stopping callback function. tf.keras.callbacks.early stopping. And here we can monitor a specific value from the model. So let's do validation loss and specify a patience threshold. I'm going to do 5. What that does is it looks at the validation loss, and when it sees that it starts to increase, it will stop the training. So when the validation loss starts to increase, that means your model is beginning to overfit, and the early stopping is designed to stop the model's training right when it starts to overfit. So what this does is it has a patience threshold of 5, which means after 5 consecutive epochs of no improvement in the validation loss, it will stop the training and it will restore the weights from the best epoch. So restore best weights equals true. Alright, let's run this. And it should train. While it trains, let's start generating the results. So I want to get the results using model.evaluate on the test images. So I'm also setting verbose equals 0 so we don't see one of these loading bars. And we're going to print out the accuracy of the model. We'll display it to 2 decimal places as a percentage and format this using the second value returned from results. So results sub 1. I'm also going to multiply it by 100 to see it as a percent. Alright, and then we'll get a confusion matrix and classification report. So for that, we're going to need to generate some predictions. So that will come from model.predict on the test images. However, I'd like to point out that the predict function here will just return whatever our output of the model is. In this case, it's a single probability value for each example. So let's take a look at that. You can see for each image we get a probability value. This isn't the same as the classification. We want to classify it as a positive, as a 1, when we have over 0.5 probability, and as a 0 when we have less than 0.5 probability. So what we can do is ask, is it greater than 0.5? That will give us trues and falses. And then we can squeeze this down with numpy.squeeze, which all that does is remove the extra dimension. You can see this is 2-dimensional. It's a little array within an array. So by squeezing, we remove that extra dimension. We have 1-dimensional set of trues and falses, and we type .asType numpy.int to convert the trues and falses into 1s and 0s. And here is a good set of predictions. Let's put that there. With our predictions, we can create a confusion matrix. So I'll use the confusion matrix function from scikit-learn. We just have to pass in the true labels along with the predictions. So the true labels we can get from test images.labels. And you can see it's a list of all of the correct, the true labels. So we'll pass that in and compare it to predictions. And I'll also specify this labels argument, which allows us to specify the order in which we'd like to display the classes. So we want to see the negative class first and the positive class second. And just to confirm that we know which of these classes is which, we can do test images.class indices to see the mapping. You can see no pollen is mapped to 0, pollen is mapped to 1. Okay, now we'll create a classification report, which I'll call CLR, and here we pass in the same thing. Except we can also pass in some target names, which allows us to give custom text labels to each target, to each label. So we'll do no pollen and pollen. Just make sure that these are in the same order as the labels you specified. Alright, now we can display the confusion matrix. So let's create a new pie-plot figure with a figure size of 6 by 6. And we'll create a seaborne heat map, pass in the confusion matrix, turn on annotations, set format equals G, which has the effect of showing the results as integers and not as scientific notation. And then we will set the minimum color value to 0, give it a color map of blues, and turn off the color bar. And then we'll set the tick marks. So first we specify ticks, which is the spacing of the tick marks. Since we only have 2 classes, that'll just be 0.5 and 1.5. The labels here will be the same as our target names. I'll just go and copy that. And then I want to copy this over and do exactly the same thing for the y ticks, since the axes should be symmetrical in a confusion matrix. Then the axis labels, on the x we have predicted values, on the y we have the actual values. And then we'll give it a title, which will be confusion matrix, and we'll show. Alright, let's see how that looks. So we have 86% accuracy, it's very good, and a pretty good confusion matrix as well. We do have some misclassifications, but in general it's doing fairly well. We can get a little more information using the classification report, so let's just print one out over here. Classification report. Put some hyphens. And then display the CLR here. Alright, and you can see the precision and recall for each class. So precision is a measure of out of all the predicted values between classes for a given class. So for example, let's look at the pollen class. Out of precision is saying out of all of the predictions we made for pollen, which is these two boxes, what percent did we get correct? That would be 83%. For a recall, that's saying out of all the actual pollen examples, which are these 2 boxes, what percent did we get correct? And that would be at 93%. On the other hand, for no pollen, our precision is 91%, and our recall is 79%. The F1 score is a sort of average between the two. So it's sort of an overall single value metric as to how your model's doing within a class. And you can see it's fairly good. They're about in line with the accuracy, which is what you like to see if you're using if there's if both classes have the same F1 score. Okay, so last thing I want to do is just do sort of like a little visualization of how the model's making predictions. So what we can do is sort of display samples from the data and then display our classifications on those samples. So we'll create a new pie plot figure. Let's give it a 10 by 10 figure size. And what we'll do is for I in range 9, so we'll check 9. We'll look at 9 different images. I guess we could do this for 16 images. So we'll do a 4 by 4 grid here. So for each of these 16 images, we're going to create a new pie plot subplot in a 4 by 4 grid, indexed by I plus 1. The plus 1 is because the subplot function requires that the index is 1 indexed instead of 0 indexed. So you can't start at 0, you have to start at 1. Okay, and then we'll use the imShow function from pyplot, which allows us to show a NumPy array or in this case I think a NumPy array, as an image. So the way we get a given image, so we want to take the ith image from the test examples. So let's look at test images. This is a generator. Now if we take the 0, if we do sub-0 on this, this will actually return the first batch in the generator. So this should be, it's actually a tuple, so I can't show the shape, but this should be 30, we had a batch size of 32. So there should be 32 images, and then paired up with, at the end, with 32 labels, one for each image. And we don't really care about the labels right here. We want to get the image data. So this isn't a tuple, right? We take the first element of the tuple, which is all the image data, and now we get a NumPy array containing 32 images. So the shape of this will be 32 images of size 24 by 24 by 3. So we want to take the ith image, so we'll index sub I here. Let's say I is 5. Then we'll take the fifth image, or the sixth image. Now each one that we index will have size or shape 224 by 224 by 3. So in here, let's show the ith image. Just change 5 to I. And let's turn off the axis. So we don't want to see tick marks here. And we will show. So this should show 16 images from the test set. Alright, and there you see, we have some bees. So I'd like to know how we performed on these images. So one way we could do this is by giving each of these a title. plt.title. And the title can be no pollen if our prediction, if the actual value for the actual label for the image is 0. So we can take the ith test label with test images dot labels sub I. We get the ith label. If it equals 0, then we'll have no pollen as the title. Otherwise, we'll have pollen. And in here you can see we've now labeled them. This is not our prediction. This is the, we could do this two ways. We could do this with our predictions or with the actual values. Okay, you know what, we'll do it with our predictions. I think it makes more sense. So instead of doing this, we'll take the ith prediction. So prediction sub I. And so this is our predictions on it. These are the predictions we made. So we said no pollen here, we said no pollen here, we said pollen over here. So we want to see if we're correct or not, and one way we can do that is by specifying a color to each of these titles. So we'll make the color blue if we got it right, red if we got it wrong. So how we can do that is we can say the color will equal blue if our label is equal to the prediction we made. So if our prediction, if the ith prediction is equal to the ith label, test images dot label sub I, we'll have blue. Otherwise, we'll have red. And this way we can see our predictions along with whether we got it right. So we guessed pollen here and it was wrong. We guessed pollen here and it was wrong. We guessed no pollen here and we got it wrong. You can see the little pollen sacs on the side. And here we guessed pollen as well and we got it wrong. I'm not sure why we guessed it. I really can't see much there. But otherwise we got it right. You can see we guessed pollen correctly and there's little sacs. Pollen correctly and there's little ones. No pollen here, but there's no sacs. So it looks like our model is performing as we wish, although it is making some misclassifications. Alright, the last thing I'll do is just give this a title. So I want to give the whole figure a title, not just each subplot. So we'll use plt.subtitle for this. So let's do sample classifications, and we'll give it a font size of 24. Size equals 24. Alright, classifications. And there you go. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.